Okay, in today's lesson, we want to spend a portion of our time looking at Young's double slit experiment. Now, based on what we have on the screen here, and before we even talk about that, last class we would have talked about diffraction, right? And diffraction is when you have a particular wave going towards a gap, and what the gap does, it allows the wave to pass through it and what we say diffract it, meaning that it spread it out. That's what diffraction is. So imagine that we had some um, waves looking like this, meeting a gap. When it meets that gap, what we observe is that diffraction takes place, which is just the spreading out of the wave. Now, mind you, in order for diffraction to occur, right, or perfect diffraction, I should say, um, the width of the gap or the width of the slit must be the same length of the wavelength, so to speak, right? So imagine that the wave is coming in or coming towards the gap. Whatsoever the wavelength is of the incident wave, that must matches up with the width of the gap in order for you to have perfect diffraction wave coming out. So with all of that being said, Young's double slit experiment is one that now kind of proves to us that um, that light goes through a process that we call interference. Now, interference, as we would have pointed out previously, speaks to when waves meet together. So waves can meet together either in phase or out of phase. When the waves meet together in phase, they perform constructive interference, right? And constructive interference is just um, thinking about the waves becoming stronger, so to speak, right? Now, when the waves meet out of phase in terms of interference, what we have is what we call destructive interference, which just simply speaks to the fact that the waves are canceling out, as the words are just destructive, right? So they are canceling out each other. And what Young's double slit experiment has allowed us to see, it has allowed us to clearly observe the process of interference. And what he was able to do was to take what we call a slit, right? So he take a slit right here that has two slits in it. So let me say, he takes a screen, right? Let's call it a screen. So screen one. Well, this is screen one. So we'll talk about why we have screen one here. And then we have screen, I don't want to call it screen. Let's call it a boundary, right? Let's call it a boundary. Now, when the wave meets this boundary, there are two gaps, right, or two slits. Now, as we know, whenever some wave meets a slit, diffraction is going to take place, which is the spreading out of the wave. So, at point B, when the wave meets the slit, it's going to diffract, clearly spreading out the waves like this. When it reaches point C or slit C, then it would perform the same process of diffraction. Now, when both of these waves meet against each other, they will either meet constructively or destructively, which will in turn show us on a screen bright and dark fringes. Now, when we talk about bright fringes, right, it's when the wave would have met constructively. So right here, you're seeing the bright light or the bright line. That is just when we have constructive, constructive interference, right? So we were able to observe this by putting a screen at this position. So this is where the screen is located. Good. Now the section that we have dark, that is completely dark, that is where we have destructive, right? Destructive interference. And we call those dark fringes. Okay? We call those dark fringes. So the whole experiment here was just to show us that when light, but not just any specific light, but a light from a coherent source, when that light is shone on a slit that, well, a boundary that has two slits or has two gaps, what we observe is a process of diffraction from the slits, and then we observe a process of interference. Okay? Now it says here that the Young's double slit experiment demonstrates interference of light from two sources. The two sources that we talk about is from this gap. So this gap right here is almost like a source, right? In a sense, we're saying that that is where the wave is coming from. So this um, gap right here is producing some type of wave, which we're going to call it the source. Similarly, this also would be a source, so to speak. Now it says that in this experiment, you can use one coherent source and a double slit in order to form a interference pattern. It says here, what if you don't have a coherent source of light? For example, a light bulb. Then what we can do is that we could have the source somewhere here, which is giving off the light. And then what we would do is to get all of that wave coming towards it. This first slit here is going to diffract the waves, right? So this single slit is going to diffract the waves. By diffracting this wave, it channels it in such a way that it has a constant frequency and a set wavelength. Because a coherent source is a source that has a fixed frequency and a fixed wavelength. So in this regard, when we don't have a coherent source, but by bringing it to this slit, right, this slit is going to make these diffracted waves become coherent. So at the end of the day, when this wave meets this boundary, it is already a coherent source. So all it just needs to do is to just diffract at this point and produce new types of waves, and then go to form the whole process of constructive interference and destructive interference. All right. This is just one way how we can look at the interference patterns. There are other ways we can look at it, and I'll show you in a short. And as it relates to the whole concept of constructive and destructive interference, there's something that I must point out, right? It says when the light source, right, when they meet constructively, we can say that the waves have a part difference, right, of n wavelength. So once the wave meets constructively, we say that the waves have a part difference of n wavelength, where n is just an integer. Good. So that is what, when we think about our bright fringes being formed, right? What we're observing is that the waves are meeting constructively, but the path difference between them is going to be n wavelength. All right. Also, when a dark fringe is formed, or when dark fringes are formed, clearly dark fringes are formed when the the light waves are out of phase, and in this case, we say that they are completely out of phase. And obviously, if they are completely out of phase, it's going to perform destructive interference. Now, as it relates to the path difference, whenever we have dark fringes, we say that the path difference, right, is n plus a half wavelength. So if you observe, or if you get a question that speaks to a dark fringe, right, and I'll show you a little bit more about what I mean. But if you get a question that speaks to a dark fringe, right, then you must remember that the path difference between the two waves that form the the dark fringe has a path difference of n plus a half wavelength. Now let's consider something here. Now this is just a different view of what is happening. So when the light wave enters, the coherent source enters the junction, or not the junction, but the gap right here, right? So we have our light entering the gap. Now, this is another way we could draw it. So rather than drawing the black and white thing around there, you could represent the fringes as such, right? We could represent the fringes as such, where we are seeing an alternating bright and dark fringes, right? So this right here is just showing us that at the center of the slits, or at the center of the slits, we would observe a very bright light, which is what we call our central fringe, which is just telling us that at the center, my waves are meeting constructively, right? And at this point, we're saying that that is when you would experience the strongest constructive interference. Now, as we move away from that maximum bright fringe, we move down right here to where we say we have a constructive interference, right? So right here, you have your first, you have your first destructive interference. So this is when the waves would meet out of phase. And then after that, we have another bright fringe, which we call it our n equal 1, which is just telling us that this is our first order of bright fringe. From central fringe, this is your zero order fringe. So n at this point, at the central point, is equal to 0. So when you hear we talk about the nth order, it is just talking about, you have to, the first one that you would count in terms of your bright fringe is the one after the central, right? So if I say, what is my, how can I say it? Let's see. All right, we'll soon talk about the whole order when we look at another scenario. But at this point, I just want you to understand that when we start counting the bright fringes, is really after the central fringe. And at that point, we say that that fringe has an order of 1. So the first fringe after the central fringe has an order of 1. Then the second fringe after the central fringe is called the second order fringe, all right, bright fringe. So, in the whole process here, we're seeing an alternating bright and dark band. This will be your bright band. Right here will be your dark. This one will be your dark, just showing us that the wave met destructively. Then we have another bright fringe. Bright fringe. Mind you that it's like a mirror effect whenever we're considering the whole interference pattern, because on both sides you're seeing a reflection of the same thing. That's how it normally works. All right, there's a reflection. So the same number of fringes on the this side is the same number of fringes that's going to be on this side as well, right? That's typically how it normally goes. Okay, now we need to consider a few things because there's a particular equation that we should derive. So I want you to understand this. Whenever let's consider this particular fringe, right? This bright fringe right here. So we expect that if they are going to, if we're going to produce a bright fringe at point Q, it means that my wave coming from this slit, right, must meet constructively with the wave coming from this slit. So that would be how the whole constructive interference occurs to form that bright fringe. Now at this point right here, at this very point AC, this is when I can say that my waves have a path difference of n wavelength. So what this is just telling us is that for the constructive interference, one wave is somewhat lagging behind, but the lagging behind effect is by n wavelength. All right. So let's see. Let's see what we have here. Let's go to this. It's the same wave that we're considering. The one that was at Q a while ago. We're just zooming in up on something here because we want to come up with an equation. Now, mind you that these are what we call our slits, right? Our slits, and it's just the gap in between the boundary. So that's the one, because it has two slits, we call it a double slit. So that's one slit, slit one, slit two. Okay? Now, just a while ago, I said that for constructive interference, right, my waves would have a path difference of n wavelengths. This is my path difference. It is just by how much my wave is lagging behind. So one wave is ahead by n wavelength, right? It's ahead by one wavelength, but it's still going to be in phase, right? So with that being said, if this side is referred to as n wavelength, and we can also look at it to say that there is a right angle triangle that is being formed right between right here. Mind you, between the waves, there is an angle between them. So just like how we have a path difference of n wavelength, there is a small angle here, right, that the waves are at each other. And we're just going to call that angle theta. Now, let's consider something here. So if we look at this triangle, right, this side we're going to call this side AC. So this length of my triangle is going to be AC. This length of my side, I'm going to call it AB. So I have two lengths so far of my side. Obviously, this side is going to be DC, but we're focused on AC and AB. Now, if we use our Pythagoras theorem scenario, seeing that our right angle is here, or we can use the whole trig ratio scenario, then this side right here will be my hypotenuse, right? My hypotenuse, based on where the angle is positioned, this side is going to be my opposite, okay? Now, with this being said, I want to highlight something here. You're seeing A right here. This A, in most cases, we call it the distance between the slits. So, from one slit to another slit, right, there is a distance between them, which we're going to call it A. In some textbooks, you'll see A being represented as D, but we're saying that A, in our case, is what we call the distance between the slits. So there's a distance between the slits. That is going to be what we call A, and that is our hypotenuse. So if A is our hypotenuse, that corresponds with AB, and AC is our opposite, which corresponds to N wavelength, then I can link my equation. So using sine theta, since AC, so since AC corresponds to N wavelength, and well, this is AC, not AB, and AB corresponds to A, then I can use my sine theta rule. Because remember, the sine theta speaks the opposite over the hypotenuse. My opposite is this thing right here. So that's my opposite. A is going to be my hypotenuse. And the whole reason why A is our hypotenuse is because of the whole fact that the right angle is here. Alright? So we can get an equation that says N wavelength divided by A is equal to sine theta. And what this equation will help us to understand is to find information pertaining to the wavelength of the wave. So that's one thing we could find. We could use this also to find N, which is the order of fringes. All right. We could also use this to find what would have been the angle theta, right, between the bright fringe, well, between the waves at the first slit and at the second slit. So that's a very important equation that we will use from time to time, and it is just rewritten as this to say that N wavelength is equal to A sine theta. Or in some books you will see N wavelength is equal to D sine theta, where D just speaks to the distance between the slits. Between the slits. And we measure that from here to here. Alright? And of course we know that lambda speaks to the wavelength. Now we'll move along a little bit here. We're going to want to come up with another equation, so to speak, that we can use. Now it says to us that for small angles, the distance y of the first bright fringe from the central fringe is given by using a particular equation here. Right? So this is what we're trying to find. We're trying to find y, which is the distance from the central fringe to the first bright fringe. So we want to find that distance y. Now, one of the things that we should see coming out here is if we were to consider a triangle in between here. right? If we were to consider a triangle in between here, a right angle triangle, and we have some small angle position here, then we could clearly find what this thing is. We could clearly find some information pertaining to y because we have a triangle right there. Let me see if I can find a much better looking thing to kind of gear at what we're talking about. So if we were to consider this, right? This is a question, but we'll soon come back to it. The question might ask us to find what y is, right? Or we want to derive something pertaining to, we want to derive an equation that we could possibly use to find some information pertaining to y, which y is just the distance from the central fringe to the bright fringe. Now, if we have an angle right here, we can clearly see that we have a right angle triangle being formed, and there is another variable that we can take into consideration, and this variable we're going to call it d. D is just the separation from the slit to the screen. So d is what we call the separation from the slit to the screen. So let's go back here a little bit. So this is my d value, right? All of this is d, okay? And we're saying that for small angles, if your angles, so this angle right here is a very small angle, and this angle here is also going to be a very small angle. If those angles are very small, then what it really means is that sine theta is approximately equal to tan theta. Now, tan theta is obviously the what is tan theta again? Adjacent over the, or opposite over the adjacent. So tan theta is opposite over the adjacent. Based on this, if my angle is positioned here, right, then this is my opposite. So that is y. Then now my adjacent to the angle is d, so it's going to be right here. So we can come up with that to say that tan theta is equal to y divided by d. But we're saying now, because of small angles, sine theta is approximately equal to tan theta. Now, if we go back to what we just derived a while ago, that says n wavelength is equal to a sine theta. If I make sine theta become the subject, I get that sine theta is equal to n wavelength divided by a. Okay? Seeing that we're saying that for very small angles, sine theta is equal to tan theta, then we could equate these. So rather than saying sine theta, we could clearly see that sine theta is equivalent to this. So in this equation right here, I can put that my sine theta is equal to n lambda divided by a. So this is what it comes down to. It comes down to this equation here. So we have an equation now that we can use from time to time, that we will use to find out certain information. All right? So be aware of that equation that we can use. Okay? Now, yes. This is just another diagram here, which just shows us the order. So at first, the brightest light that is formed is what we call the central fringe, but that fringe has a order of 0. What that really tells us is that there's no path difference between the two waves that form that met constructively, right? So there's no path difference. They are completely in phase. So because they are completely in phase, because they're completely in phase, then there's no need for us to say that there's a path difference of n wavelengths. So that is the reason why we don't have n that's the reason why we have n equal to 0, because they met completely in phase, all right, to form that bright fringe. But now when we look at this one now, right, we can clearly see that the second bright fringe is of the first order, which just tells us that n is equal to 1. So our waves, our bright fringes, when they are our waves, when they meet constructively, this is just telling us that the path difference, right, has a distance of n wavelength. You understand? N wavelength. Then now when we consider the second order, this is just telling us that the path difference is much wider by a factor of 2, which is just telling us that it has an order of 2, so to speak, and n equal 2, right? So that is what it is really telling us. And with that being said, the further away you go from the center, your bright fringes becomes much duller in a sense, meaning that the further away you go, the intensity of it is going to die down, as you could see from this right here, that they're currently decreasing, right? So that increase in path difference now is just really reducing the overall interference, constructive interference as we go along further out. All right. So let's just identify what y is. Y is the distance between the nth order bright fringe and the central fringe. A is the distance between the slit. So right here is where A is located. Now D is the distance from the slit. So from here, from the slit, from the center of the slit to the screen. So wherever we're seeing the waves, right? So your central would be somewhere here. Right? So that would have been your screen. Let's trying to draw something. So once you're seeing these waves out here, then this thing right here is what we call a screen. Okay? And n now just speaks to the order of bright fringe. So those are the variables. So we came up with an equation just now that says n wavelength divided by A is equal to y divided by D. I believe that's how the equation was, yeah. And it's an approximation, right? It's an approximation that we are considering here. Now let's see if we can put things to practice a little bit, right? All right. So it says that light of wavelength 600 nanometer, right, from a single source passes through two slits that is 0.1 millimeters apart from each other. It says an interference pattern is seen on a screen 1.1 meters away from the slits. It says how far is the second order bright fringe on the screen from the central fringe, right? So we want to find that information. We want to find y. Y is what we want to find. So we could start out by using this is with this question now. If you're not given an angle, then quite frankly, um, you would not use this one. So you would not use sine theta. Alright, A sine theta is equal to N um, wavelength. We won't necessarily use this because we don't know what theta is in this case. We can find theta, but we don't know what it is. So obviously we need to use this one that says N lambda divided by A is approximately equal to Y divided by D. But let's write down what we know. We know that N is equal to 2 because it says the second order bright fringe. Then also we know that lambda is 600 nanometers, which is the same thing as saying 600 times 10 to the minus 9 meters. Also, we know the separation between the two slits, which we're going to use it as A. So A is equal to 0.1 millimeters, which is the same thing as 0.1 times 10 to the minus 3 meters. Also, we know the distance between the slit and the screen, which is what we call D, and that has a value of 1.1 meters. All right, so let's see. Let's see right here what we have going on. Okay, so let's see if we can find Y. I think I'm going to need some space here. So let me just erase this and bring it up further. So let's bring up our equation again. So N wavelength divided by A times D is equal to Y. N is equal to 2. 2 times the wavelength, which is 600 times 10 to the minus 9, times D, which is 1.1. Divide that by A, which is 0.1 times 10 to the minus 3. We can go ahead and work out the constant. So 2 times 600 times 1.1, that gives me 1,320 times 10 to the minus 9. Then now I'm dividing the constants down here. Divide that by 0.1. When I divided everything, when I divided 1,320 by 0.1, I got 13,200. Mind you that there is a times 10 to the minus 3 in the denominator, which just tells us that we could bring it up in the numerator, right, by saying minus 3. Okay, so we have 13,200, right? And then I would have need to finish work out the power right here. So this is going to be 10 to the minus 9 plus 3, which I will really leave us with 10 to the minus 6. So we have 13,200 times 10 to the minus 6. So let's see what that is going to give us overall. E to the minus 6. So this is telling us that Y is equal to 0.0132 meters, all right? Which is very small, which is what we expected, all right? That will be about 1 centimeters away from the central bright fringe. That's where you would observe your second order of bright fringes. All right. Okay. Yeah, I won't do this question. I won't do that one. But let's talk a little bit about what we call diffraction grating. If you check your textbook, you will find out some more information about diffraction grating. But it is just um, you can research it too. So diffraction grating is a slide containing many equal spaced slits very close together. So it's a piece of so you see it's just like a piece of material that does have a lot of gaps in between it. All right, and it says when monochromatic light is passed through a diffraction grating, the interference pattern is much sharper and brighter, right, than it would be when we pass the monochromatic light through a double slit, right, or using Young's double slit. So what we're really saying is that if we want to observe the patterns much better, you understand? Rather than using a double slit, which is just two slits, we could use what we call a diffraction grating, and it's a piece of material. So a diffraction grating is just a piece of plastic that contains a lot of spacing in between it. You understand? And we're saying right here that if we were to consider uh, a diffraction grating that has 50 um, slits, if it had 50 slits, you would observe a much more defined bright fringe. You understand? Versus when you consider um, a what we would say now, if we were to consider a diffraction grating with a much lower slit, this n right here speaks to the number of slits, and that is 20. So the fringe is not so much well defined. It's somewhat much bigger and not so quite defined. But the other one now that uses 50 will give you a more better pronouncement of the interference patterns. So that's just the overall advantage of it. You understand? So with the diffraction grating, you're going to see a lot more patterns being formed, a lot more bright fringes, and they're going to be well defined. Now, let's try to understand how a diffraction grating works. It says monochromatic light is incident normal to a diffraction grating with 7 times 10 to the 5 lines per meter. A second order maximum, which is the same thing as what we call second order bright fringe, is observed at an angle of diffraction of 40 degrees. It says calculate the wavelength of the incident light. So this is a question that we can get from time to time. All right? And what this question just wants us to do, we must first understand that there's a relationship between the slit spacing and the number of lines per meter. So I want to know what is the slit spacing between each diffraction. So let's consider something here. Let's imagine that this is my diffraction grating. On my diffraction grating, there are several lines on it. There are several lines, several slits. I just want to know the distance between the slits at this point, because that is just significant to me. I just want to know that. Okay? So let's consider something. We want to know how much does one slit represent first. We want to identify that. All right? So it tells us that the relationship between the slit spacing, and we're going to use A as our symbol, slit spacing A and the number of n lines per meter is given by this, to say that um, because we're considering 1 meter per meter, then A is equal to 1 meter divided by the number of um, lines per meter, because n is really the number of lines per meter, all right? And one here just speaks to the 1 meter, because we're considering, let's take it. So for every 1 meter that we have a total number of 7 times 10 to the 5 lines, right? So for every 1 meter, we have that number of lines. I just want to know what is the spacing between each line. So I have to take that 1 meter and divide it by the number of um, lines per meter to find out the spacing. It's almost like a graph paper. Like, let's take, for example, you have a scale, right? And you're going up by an increment of 4, right? Now, in between here, you have 5 small boxes. So 1, 2, 3, 4, 5. You have 5 boxes. And you want to find out how much does one box represent. You understand? So you would have to consider count the number of boxes, right? And divide it by this amount. Divide it by the unit that you're going to buy to find out how much the box represents. So the total number of boxes divided by divided by the overall number that we're representing the scale by will tell you how much one of these represents. So let me see. So because we have 5 boxes, right? So the number of boxes is 5. So it means that each of these boxes, right, is going to represent 1.5. So each represents 1.5. Let me just see something here. Give me a second. No, it's not going to represent. I don't think it's going to represent 0.5. Right. So 0.8 times 5. Okay. So in this case, that's not what we're supposed to do. So it's like considering this. Let's consider something else just to see if we can get it properly. Imagine that you're buying some mangoes, right? So each of these boxes represents some mangoes. So you have 5 mangoes. You have 5 mangoes, and you paid a cost of $4 for the 5 mangoes. So in order for me to know the cost of 1 mango, I have to take the total mangoes and divide it by the amount that I paid for it. So let me see if I'm right. So I want to know the cost. So the cost price divided by the amount. So 4 divided by 4. That's the right way of saying it. So the total amount that you would have paid for it divided by the amount would tell you how much it represents. So in this case, we're saying that that for 1 centimeter, there is a total of 7 times 10 to the 5 lines, right? That's the amount of lines that is within it, and I want to know the space in between it. So I would have to take that 1 and divide it by the number of lines. All right? Hope I didn't confuse anyone. But that's just what we're saying here. So let's see if I can go back over it. So if you have 5 mangoes, right? And I want to know how much does one mango cost. I have to divide the cost by the total number of mangoes. So my 5 mangoes cost $4. I want to know how much one cost. In this case, it's going to be 0.8. Each of these boxes is 0.8, 0.8, all the way up until you reach 4. All right. So that would explain that. So in this event, if 1 centimeter, if 1 meter has a total of 7 times 10 to the 5 lines, then for me to find out what is the distance, or what I would say A, if I want to find A, which is just the separation between the gaps, then I simply would have to divide 1 by that total number of lines. So we're saying that A is equal to 1 divided by 7 times 10 to the 5, right? And when we do that mathematics, we're getting a value that says A is equal to 1.43 times 10 to the minus 6 meters. So this is now your separation, your slit separation distance. All right. So we know that information. We want to find the wavelength. That's what we want to find. We want to find the wavelength of the wave. So it means now that we have to take into consideration an equation. One equation that we can take into account. But before we take into account that, let's write down the things that we know. We know A, right? We don't know the wavelength. That's what we're trying to find. We know an angle, which is that angle is 40 degrees. We know that n is equal to 2 because they said the second order maximum. So then the equation that we can use is that says A sine theta is equal to n wavelength. All right. So in this event, we want to find wavelength. So wavelength is equal to A sine theta divided by n. So we can put in that value. A is equal to 1.42 times 10 to the 6 times the wavelength. Well, not the wavelength, my bad. Sine of 40, right? Divide that by 2. Let's see right here what we're going to get. I'm just writing down something here. Yes. So if you go ahead and try this out for yourself, you're going to get a value that possibly looks like this. That says 4.69. I would believe that what you would get, times 10 to the minus 7 meters. And quite often with wavelengths, light and a hole have a wavelength in nanometers. So we can make this become nanometer by moving the decimal point 2 times. If I move it 1, 2, it means that I have to subtract 2 from my power. So it now means that my wavelength is equal to 469 times 10 to the minus 9 meters, which is the same thing as saying 469 nanometers. Okay? Go ahead, solve this one for yourself. And of course, you would give me the answer. All right. So take down that one and do it for yourself. Let me see if there's anything else. All right. So that would complete it. So go ahead and do that for me, please, so that we can see if you understand.